right, hold on. The meeting is being recorded. And now I have to change slides. 1 second. We're almost there. Help. That's fine. Yes. And no, that's fine. That's fine. Yes. Okay, that's good. Yes, no problem. All right. So thank you so much. Thank you for the kind introduction. I'm super excited to give this talk because in 2003, which is 10 years ago or 20, this was actually my first conference. So I arrived in California and my advisor said, oh, why don't you come and give a talk? And so I came to this wonderful place. It's a great venue. It's so beautiful, and I'm super happy to be here. And thank you for the organizers for inviting me. So I will be talking about, I changed my title a little bit. So foundation models, generative models, and inverse problems. And I want to emphasize, first of all, that this is the work of many, many students, including Jill, Yanis, Sriram, George, and listed here in the first row. Colleagues from UT Austin, including Eric Price, John Damir, Adam Clivans, Konstantin Karamanis, and Sanjay. And also collaborators from MIT, and also the Datacom project it was led by Ludwig Schmidt, and it also has a very large team of students and collaborators that I will be talking about. So, and this is also work that has been supported kindly by NSF and the Institute for the Foundations of Machine Learning, the IFML Institute that I'll be talking about. So, very briefly, I want to tell you a little bit about foundation models. And everybody knows, like in November 22, there was this paradigm shift in the world where, I used to need to explain what generative models are. I don't need to explain what generative models are. Everybody, like, my grandma knows what generative models are right now. So this is a very bizarre thing for me that has never happened before. And ChatGPT was a historical thing. I don't think any other product has gotten to the hands of millions of people so quickly, right? It was a historical moment. But also StyleGAN 2, which generates images, DALL-E 2, and so on, which is a text conditional model, but also less known Clip, Whisper, SAM, Dino, and so on are all foundation models. So a foundation model can be generative, which means it can produce pixels, images, or it can produce audio, or it can produce text. Or it can be a classifier like Clip. Clip is a model that takes images and text and tells you how well this image matches to this text. It's still a foundation model, even though it's not generative. A common denominator is that all the foundation models are trained on a different scale that we previously did, right? ImageNet was in the order of 1 million images, right? But now these are trained at billion scale, and that seems to create new behaviors. And that is fundamentally important, I think. So another problem is that most foundation models are closed. They're closed either behind an API, or maybe there's code but not a data set, or so there's different levels of licenses and different levels of closeness. But in order to have a competitive research ecosystem and an industry ecosystem, I think it's important to have open foundation models and open data sets. And we're working for that. And that's kind of the first part of my talk is about how do we create large open multi-model data sets and hopefully models. The biggest bottleneck for creating the models has been to create the data sets. So I will explain a little bit, that's the first part of my talk. So in our institute, IFML, we are creating new foundation models and new data sets. And also I call the second part of my talk, teaching foundation models new tricks. So foundation models can produce images of dogs, but can they produce images of my dog, right? So or can they deblur an image, or can they accelerate MRI? So this is the second part of my talk where we call it teaching foundation models new tricks. And this is algorithmic innovation. So let's go back before foundation models to tell you what I think is the reason they are so important. So before, if you had a problem in your life, like you wanted to accelerate MRI, you would take a data set, and train your model and move on, right? If you wanted to classify bananas, you would need a lot of labeled bananas. and you would train a banana classifier and move on. But you would need thousands or hundreds of thousands of images, of labeled data sets. Foundation models solve this problem, right? Because you don't need, let's say you want to play Scrabble, right? Or you want to play some new game you invented. You can create 20 examples and feed them in ChatGPT in the prompt. And just with few shot learning, it will learn to play the game you want reasonably well. So there's these few shots emergent behaviors that are allowing us to solve problems now with a few dozens of labeled examples as opposed to thousands. So that is, I think, the most important paradigm change. The other issue is classical machine learning had a lot of problems. For example, it was fragile to spurious features. So there's a whole area in AI and ML where you say spurious features or domain changes and so on, where you train your model to recognize camels, but all your camels were in the desert. So whenever it was finding, a camel in a forest, it would misclassify, or the accuracy would drop 20 points. But right now, foundation models magically don't seem to have that problem just by diversity of the training set and just by diversity of the task. Similarly, there was fragility to the changes in distribution, like lighting conditions or camera types or imaging protocols in MRI and so on. And these papers that I have listed here have recognized those issues, but we are finding that just by scale and just by diversifying our data sets, most of these problems are significantly reduced. They're not completely solved, but they are much, like foundation models trained on a variety of data sets are much more robust just organically. So the central dogma in my lab, this is like the joke my students have, is that they say, you separate the foundation model that knows the statistics of whatever you're doing from the inverse problem you want to solve, right? So this is in sharp contrast with the canonical paradigm where you just train your model to go from measurements to reconstructions or to go from blurry images to clean images. Right now I'm saying, learn the statistics of clean images. And then when you see a blurry image, run some optimization or some Langevin dynamics or some other algorithm to produce an image that both explains the measurements and solves the inverse problem. So this has been kind of a central paradigm, and I will be talking a lot about that. So separate the physics of the forward operators from learning the statistics of your data. And learning the statistics of your data is done by the foundation model, and a lot of people are spending millions of dollars training the foundation model. So that allows you to ride that train and benefit from better priors, essentially. So that's kind of the most important message that I have is this is a very powerful way to ride on this revolution that's happening now. And for me, this started in 2017. So I'll tell you a story. My inspiration for this kind of paradigm was actually by papers by Marco and Chinmay and Rich Baranyuk, descendants and students, essentially. So these two papers specifically were my inspiration. So I'd like to tell you about them. So these papers were coming out. I was working on compressed sensing back then. And it's a beautiful paradigm to do nice, clean theory where you're trying to recover a sparse signal. But these papers were saying, okay, it's not just that the signal is sparse, there's additional structure, right? There's additional structure in this supports, for example. How can we leverage that and do better, right? So that kind of got me thinking, okay, we can model this support structure by trees or graphs or something that we postulate, but let's make it data driven, right? So I thought about, let's make the structure coming from a pre-trained foundation model. We didn't have the words foundation model back then, right? It was basically a GAN that was too expensive for me to train, right? So I couldn't train DC GAN or style GAN in my lab, but I said, okay, this style GAN knows how faces look like. And now I don't want to just generate some random face. I want to in-paint half of my face, right? So I'm deleting half of my pixels. If I put some random Z into the generator, it's going to spit out some random face. Okay, fine. But now I'm going to do gradient descent in the latent so that the face matches half of my face, right? That is essentially the idea of this CSGM paper, the compressed sensing with generative models paper that we did in 2017. And of course, the other good news is once you think about it in this terms, you can extend the compressed sensing theory. The compressed sensing theory tells you how many measurements do I need to find the correct support? And there's n choose k and gives you k log n over k and all this RIP stuff that you may be familiar with. And the same technology, the same mathematical technology directly translates when the world is, the priors are now deep generative models. So that's kind of what we did then. And that was when this paradigm changed. So since then, my lab basically has followed what the best foundation models have been doing, right? So the best generators for images were GANs. Then for a while, we experimented with flows. Then we moved into diffusions. And now we have moved into stable diffusions. And later, we may be moving into LMMs. And you may think that's a typo because you're thinking of LLMs. Has anybody said LMM in this conference yet? Nobody has said LMM. Okay, LMM is the new LLM. Okay, LLM is right. So LLM is a large language model. LMM is a large multimodal model, right? And I will explain what it is, but it's basically when the models become multimodal. They accept images and text, and that's kind of the trend. That's like the latest and shiniest new thing. So maybe, we can start thinking about how to use these as priors for solving our inverse problems. But right now, I will be talking about diffusions and stable diffusion. Stable diffusion is a latent diffusion. That's why it's different. All right. So, and ideally, the good thing about the paradigm of the central dogma, maybe I can go here. The central dogma says, as I said, separate your foundational model knowing the statistics of your images from the inverse problem solver. And that allows you to develop, hopefully, some theory, some sample complexity bounds for your flow or your GAN or your diffusions. And this is the kind of work that my lab has been doing, and also several others have been making good progress, because it's a clean way to separate physics from the statistics of images. So this is an overview of my talk. The first part will be, how do we create large multimodal data sets? And I will specifically talk about Lion and Datacomp, which are the projects. The Datacomp has been the project we have been working on. And the second part of my talk is more algorithmic, more classical signal processing, much more related to the first part is basically a lot of engineering and some community building. So I will explain that. But the second part is much closer to the usual things we're used to doing, where you say, okay, I have now this model, it knows how images look like. Now I want to solve a deblurring problem. How do I do that, right? And I will explain how we can do in painting, how we can enforce consistency, how we can train with corrupted data, and maybe how we can teach custom concepts. So these are kind of, I probably ran out of time, so I maybe skip one of those. So let's get into our first, the first message is the dawn of LMMs, large multimodal models. So the most common one is called GPT-4 Vision. It has rolled out in the recently, I think 1 month perhaps. And this is basically what it is. It's GPT, but you can also upload images like this one. And you can ask GPT, hey, look at this CT scan of lungs in the image below and tell me what's wrong. And this is the answer. There appears to be multiple areas of consolidation and ground glass opacities, blah, 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 blah. Okay. So this is from this paper, by the way. And there's many others. And you can also use, like, I have been able to use GPT-4V in the premium OpenAI subscription. Now, when I showed this to doctors, this image and this description, they told me this is actually wrong. This is not a correct. So, we don't have to fire all the doctors yet, but this is basically a paradigm change where you're now discussing the same way you were writing text, you're now discussing with images and text, okay? And what is soon going to be happening is it will also be able to generate images, right? So you would say, generate this CT scan if this person was healthy, right? So that's a fancy inverse problem where you have actually a language model, you have images, and you say, if this person was healthy, how would this CAT scan look like? So these functionalities are being developed right now. I don't think it has shipped, but I think it will be shipping very soon. And it's not perfect, but this is kind of, I think, where things are headed. So what I cared about the most is, okay, this is great, OpenAI is doing this, but how do we do research on this stuff? We need large, open, multimodal data sets. Multimodal means, in the simplest form, image caption, right? It can also be image caption audio or image caption time series, image caption HTML, or there can be multiple modalities. But for now, we're just working on images and text. So the text hopefully describes the image, right? So the Lion dataset, I think, has been the most important contribution in this space. And how many people here have heard of the Lion dataset? Please raise your hands. Very few, yes. So it's shockingly not known, but it's shockingly important, because the reason we have stable diffusion and open clip and all those things is because of Lion. Lion was used to train stable diffusion. So what is Lion? Lion is 5 billion image caption pairs collected from the internet. Your photographs are probably in Lion. Have you uploaded any images on the internet? If you have, there is an alt text that comes in the HTML, and Common Crawl has been a nonprofit that has been scraping the internet and creating a huge database of all the HTML. And then that HTML, basically, Lion collected only the subset that has images, and it kept the image and the alt text. And the problem is that most of the captions are not very good, right? When you upload an image of your dog on Instagram, you don't say, this is an image of a Labrador, blah, 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 right? You say, this is Bob, isn't he cute, lol, 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 right? So the caption doesn't match very well an image of a Labrador. So the problem in Lion is most of the captions are not very good, okay? So dataset creation at internet scale is actually dataset filtration. So that has been, how do we filter out of these 20 billion image caption pairs, 5 billion that are actually not terrible, right? And not terrible means we have to remove NSFW, nudity, violence, and all these things. In addition to that, we have to actually keep the captions matching the images. And the answer is we use machine learning models to do that. Models are creating the filtering that's creating the data sets that are training the new models, okay? So there's a very bizarre situation going on. Clip was used actually to create Lion, and Lion was used to train OpenClip, which is the best classifier we have openly right now. So Lion then was used to train Stable Diffusion, OpenClip, and numerous other world-changing projects, and it's used by everybody that I know, including Anthropic, Apple, OpenAI, Google. Google Imagine, for example, was trained on Lion and so on. So this has been the foundational data set that all the image generators at the billion scale have been trained on. It won the NeurIPS 22 Best Paper Award. And then the question is, okay, what's next after Lion? So the project that we are working on in IFML is the next generation of Lion. So we call it Lion 2, but we didn't end up calling it Lion 2, we call it DataComp. Because instead of just being a data set, we thought of making it a competition, because the problems of dataset curation and dataset filtration are traditionally seen in academia as very boring, okay? They're like, who wants to clean data? That's like the worst thing in the world. So instead of, and it also involves a lot of tooling, a lot of pain, and very little ideas. So we wanted to create the tooling and leave room for the ideas, and also to create a community so that people can try different dataset curation techniques. And we host like a workshop and like a leaderboard. And so a community basically that people work on dataset curation problems. So the way DataComp works is we have created a pool of billions of image caption pairs, again, from Common Crawl. And the job of somebody who's creating a dataset is to select a subset. And if you pick a smaller subset, you get more compute. Let's say you play in the 13 billion category, you have 13 billion gradient descent steps. So if you select 13 billion, which is the whole data set, you will do 1 step per image. But if you select half, you will do 2 steps per image. So you basically constrain the total amount of compute. So we give you the fixed training code. So we fix the models, we fix the training code, and we fix the evaluation code. So once you have selected your data set, you will be evaluated on ImageNet Zero Shot and 38 other benchmarks, including benchmarks that involve equity in machine learning. So as you may know, for example, in object recognition, in people recognition problems, people of different races have severely less accuracy So some of the benchmarks that we have in evaluating a model, a clip model, involve how equitable it is for people of different races, for example. So there's 38 benchmarks. And the other thing we did is we also detected and blurred faces on the pool, which makes Lion a usable data set by many companies, because many companies like Apple could not use Lion because it had personally identifying information because it was scraped from the internet. So we created all this metadata to make it easier for people to use. So this is data comp. We have a leaderboard, and if people are interested in being involved, I'll be very happy to help. It was a very large effort for more than 30 students across many institutions that made this possible. And it's a running competition now. So that was the first part. And the second part is, okay, that's cool, but now how do we do some algorithmic signal processing stuff that we know how to do, right? So I'm going to focus on, here is what I tell my students. If you wanted to try an algorithmic idea, right? So maybe you have an airplane and you want to show that an airplane can land in the sea. You can build a toy airplane, train it on MNIST or CIFAR-10, and run your benchmarks and show it lands in the sea, right? Which is valuable to showing that airplanes can land on the sea. But if you start with something like Stable Diffusion, you should think that you start with something that costs multiple millions of dollars. So now making that thing land on the sea is a much harder problem, perhaps, but it's also a much more impactful thing, because now this will be a much more capable model out of the box. So you're leveraging the power of the pre-training. And this is the research direction. How do we repurpose these massive models to solve new problems? And the central idea is you go in this big thing, you open up some layer, you get some wires, and then you run some sort of gradient descent, basically, right? Or you fine tune it in some funny way, maybe low rank, and that's kind of I think a lot of interesting problems. How do you open up these big boxes in only a small part and make them do something new? So let's focus on our first problem, which is PSLD, posterior sampling for latent diffusion models. How do we solve linear inverse problems leveraging a latent stable diffusion, a latent diffusion model? So this will appear in NeurIPS in 1 month. So stable diffusion is a generator of images that takes text as an input. It has this very complicated looking architecture, but basically it is 2 parts. It's an autoencoder that takes an image, it passes it through, it creates a latent vector Z, it runs a diffusion process in the latent space, and then it takes a decoder that goes back to pixels. And it also has a second language model that says, when you say, give me an image of a banana dancing over an airplane, this text encoder takes that and produces a vector, and this vector is entering here. So you can see how it's entering in this diffusion process. So the reason people are moving to latent diffusions as opposed to pixel space diffusions is that they are much faster and memory efficient compared to pixel space. They're basically, the dimensionality of the Z vector is much smaller, and the diffusion is much faster. It also needs smaller GPUs. By the way, you can run these models on a single GPU. You don't need to have a huge cluster. If you wanted to train this thing, it's a different story. But running it, you just need 1 GPU. It's very, and in fact, now you can even run some versions on CPU. So it's actually very easy to run these models. So stable diffusion is the state-of-the-art open foundation model for generating images. It's in general domain, and it was trained on Lion. And as I keep saying, it can generate cool images, but we want to solve inverse problems with it, like in Paint. So let's be clear. Payman also, I think, I suppose he explained problems like in painting or deblurring yesterday, perhaps. But I'll explain what in painting is. You just took a photograph like this teddy bear or something, and you don't like the stop sign. So you just take a brush and you mark it out and you say, I want this gone. It's what Google calls, I think, magic eraser, right? So you just mark this and you want it gone, right? So now you say these pixels are missing. Let's fill in these pixels using the statistics of nearby information, but also using the knowledge of images. So you see, it's not perfect, but it's pretty good, right? Similarly here, you may have a dog and a teddy bear. You mark this and you say, I want this gone, and it fills it in. And it fills it in with grass. And again, you may be able to see it, so it's okay. It's not the best in painting model there is. There are custom in painting models that are better in a domain like faces or MRI. But in a general domain, when you have an arbitrary photograph you just took, stable diffusion is the best thing there is as far as I know, right? So you need to use something that has billion scale to do it in an arbitrary set of images. So we were able to do this in my lab, having only a few GPUs, because these are results from our paper, because we leveraged stable diffusion model, right? So in painting means given an image with missing pixels, complete the pixels to preserve the statistics of the image. And this is a missing data problem, of course. And a lot of people have studied in painting before, obviously, right? So this is in painting using pre-trained generative models. And the state-of-the-art technique before our work is this DPS paper, diffusion posterior sampling, which appeared in ICLR 2023, and it was performing very well. But the problem it has, as I will show you, is it doesn't work when the diffusion is happening in the latent space. That's the technical idea of what we discovered. And there's many other techniques that we compare against that were having also very good performance. So the foundational idea is as follows. So to remind you, the pixels are encoded into a latent vector. Then a diffusion is run in the latent space, and then that latent is decoded back to an X-hat reconstruction. The encoder is a many-to-one mapping because it goes from high dimensionality to a low dimensionality. So there is many images that have the same latent Z, okay? The diffusion is happening in the latent space, which is the low dimensional space. So these are the key ingredients to realize. And now you have an inverse problem. So you say, I have this is the image I don't get to observe. I observe A times X0, A is called the forward operator. This can be a blurring operator or a matrix that drops some pixels if you have in painting, or in MRI, this is like a subset of the Fourier matrix, right? So a gazillion problems can be written in this linear inverse problem notation. And the question is, I observe Y, I want to find X hat that matches the measurements and also has high likelihood under the likelihood model that I have. The likelihood model that I have is this diffusion model, right? So in order to solve these inverse problems, we use this conditional reverse SDE. So this is a stochastic differential equation. This is complicated. There's a lot of complicated math that gets you to this point, basically. But you don't need to worry about them on a first reading. The things you do need is this thing here, which is called the score of an image. And the diffusions provide this. There's a neural network. You just plug in an image, you get this score. And the score is the gradient of the log likelihood of an image. It's actually another image, okay? So what this is doing is it's telling you how do you change your pixels so that the image becomes more likely. So you can think of this as a denoiser, essentially, right? And I think Peyman yesterday explained the connections of a denoiser to a score network. So the problem is this. This is now the conditional likelihood, right? The probability of observing these measurements given this current estimate image. So all the papers that are solving inverse problems using diffusions are working on how do you approximate this conditional likelihood term. And there's different approximations that lead to different papers. So we just took the best method at the time, which was DPS, and we ran DPS in this latent space. Nobody had run DPS in the latent space before. And just to be clear, nobody said, the DPS paper didn't say to run it in a latent space. They said run it in the pixel space, and it was very good. But we used it off-label, so to speak. And what we discovered is that it leads to bad Z vectors. So what's happening, we think, is that as you take your image, you encode it, and you run this diffusion in the latent space, you drift into bad Zs. And then when you decode back, you get bad-looking images. So here is an example of this. So you can see here is an image, and we are removing these areas, and we run the previous state-of-the-art, which is DPS in stable diffusion, and you see how it produces this funny in paintings. It's doing pretty well in the desert part, right? No problem here, but in the face and in the hands and in the fish, it's not ideal. And similarly here, you can see it's kind of doing very funny things on the face. So that's kind of running DPS in the latent space out of the box. And that led us to our key idea. We said that, okay, how do we fix this? The first thing is, what do you want from your image? You want your image after you encode it, you get a latent, you decode that, you get back an image. You would like that to be equal to the original image. This is how the autoencoder is trained. This is the definition of the autoencoder, right? This thing is kind of the inverse process. You say, take a latent, decode it to get an image, and re-encode it again. You would like this to be equal to Z. What turns out is happening is there are Z's where this is true. They're fixed points of this encoder-decoder process. And there are Z's where this is not true. We call these Z's bad Z's, all right? So I want to also say, the way this research is done is you download this $1 million neural network, you start messing around with it. So think of it like the space station, right? Like somebody built this very complicated piece of equipment and you're just messing around with it to explore what's going on. And you just test this and you realize this is not true for many latents. So you said, oh, we need to change the air conditioning unit of the International Space Station, right? But I'm not building a new space station. I can't afford to do that. But I just realized that there was a little funny thing with the latent space of it. And we just added this term in the loss that enforces the Z's to be actually good Z's, which means they're fixed point of this reverse autoencoding procedure I described here. So we call this basically the gluing loss. There's some more math that I won't get into, but the intuition is in pixel space, you will want to project on the measurements and do a gradient step to increase likelihood, project on the measurements, do a gradient step to increase likelihood, and so on. So gluing is like that, but it's in the latent space. So it explicitly uses the encoder and the decoder of the stable diffusion. So after doing that, this is our method, which produces much better reconstructions. Again, you can see this is the original measurements. This is the previous DPS method, and this is our method, which produces better results. Does that sort of make sense on a high level? And I can take questions. I can take questions now too, if people want to. Or should we take questions now? Or anyway, what's up? At the end. All right. So we have plenty of time. So here is the same technique used for deblurring. So this is, again, a very challenging deblurring problem because it's in the arbitrary domain. You can take your own picture and upload it, and you see what you get. Much harder than deblurring faces, right? So here is the ground truth image. This is DPS, and this is our method. It's a little bit better than the previous one. So we did a detailed quantitative comparison, of course, where we measured various metrics like PSNR and LPIPS and SSIM, and we do much better. And basically, we do much better because we just have a much better prior, right? It's not rocket science. And even when we focused on running it on a latent diffusion with DPS, so we have exactly the same prior, we still do a little bit better. But most of our benefit is because we use a very powerful foundation model as our prior distribution. We also have a web demo where you can upload your own images and remove pixels and get it. It's slow because it's hosted on one A100. So, if we wanted to host it on a bigger scale, we need the GPU cost. But it seems to be working reasonably well. And very recently, after we wrote our paper, which, as I said, will appear in NeurIPS, Payman's group with Mauricio did prompt tuning, which is an extra trick on top of that, and they actually did much better than us. So this appeared just very recently. So there's two very, very recent papers that built on our paper, as far as I understood, and do much better, but I haven't studied them. If anybody is here, I would love to learn how exactly they work. But the point is there's rapid progress in this space. So another second idea I want to tell you about is this consistency issue and how to mitigate consistency drift in diffusions. So this is from this paper that will appear again in NeurIPS in December. The true score function that we use is connected to the optimal denoiser by Tweedy's formula. So this is the key idea that's used in training diffusions. Essentially, you train a denoiser by using supervised learning, and then you have the score. But the problem is when you're optimizing to learn this, you're not perfectly learning it. You're doing a reasonable job, but there's some errors you make. So diffusions learn approximately the score. And we discovered that errors in the score introduce inconsistent trajectories, okay? So we defined the concept of consistency. It's basically a martingale condition. And we said this should happen, but then when we measured it, it was not happening. So I will explain the idea here. So this is from another paper that discusses different types of consistency in diffusion. I won't explain everything here, but as you're running your reverse SDE, you could run it multiple times, get multiple points, average them together, and see if the average is exactly equivalent to the one-step denoising starting from the beginning to the end. And that's the consistency condition that we showed. So we showed here. So I'm skipping the details, but this is the consistency term that we discovered should hold. The average of the SDE solver when you run it multiple times should be equal to the one-step solver in one step. So we measured this gap, and this is what we're showing you here. This is the gap of what should be zero across the amount of noise that is added in an image. And we realized that, so as I'm saying here, starting from XT, we denoise it to time zero. And if we run this stochastic sample multiple times, the average should be equal to H of XT, but it is not. So we added a new consistency regularization term, and we get much better diffusion models. Not much better, a little bit better, actually. So the cost is the sampler, you have to run it multiple times in average. And these are some results from our paper. And you can see the images on the top. So I asked my student, okay, what's wrong? This is the baseline, EDM. It's a very, very good paper by NVIDIA. And this is our reconstructions. So I asked my student, what's wrong with these cats? And he said, the first one has an eye problem, but ours is better. And this one has a weird body that's moving from the left, while ours is better. And here the body looks like a big lion body, but ours is better. So it's a little bit better. And the FID scores that we measured are a little bit better. The main point is we realized the mathematical property that should be there, but it wasn't there because of error accumulations. And then we added an extra term in the diffusion. Again, the same idea. Take this big boat, find a little thing you can fix, and try to improve it. So the general philosophical idea. So final fun story is a pre-trained stable diffusion can produce a painting of a dog, right? But what if you wanted to produce a painting of your dog, right? It doesn't know your dog unless your dog is very, very famous. So the point is, how do we teach stable diffusion to know your dog? So the ideas here are called dream booth and textual inversion, and our paper is called multi-resolution textual inversion. All of them are variations of the following key issue. So you have a picture of me. So let's say you want to generate an image of Alex Dimakis, right? And stable diffusion, unfortunately, doesn't know me. So I'm not famous enough. It knows Barack Obama, but it knows famous people, but it doesn't know me, right? So I would still like to learn me. So I'm saying an image of XX. So this we call a pseudo word, right? We're going to basically take a vector and we're going to think of this not through the language model, but as a vector that we will optimize. We're going to learn it, okay? So you basically take my photograph, you feed this prompt into stable diffusion, you freeze the whole stable diffusion box. And the only thing you're looking at is this, we call this Z. And you can perform the CSGM, the comprehensive sensing with generative models idea, to do gradient descent so that the generated image as a function of this Z, which is the description of that vector that learns me, is minimized. So after I do that, I have learned a vector that when I put this vector into stable diffusion, it produces my images, okay? And now I have this pseudo word. And now I can compose new sentences like XX is playing with cute dogs. And I've never messed with a stable diffusion box, and I get images of myself playing with cute dogs. One problem that this technique has, by the way, is that if you wanted to say Alex is playing with Barack Obama, it doesn't work. It actually takes over everybody. So in our experiments, and I think also many other people are trying to do this to learn multiple identities. So you want to learn Alex and Chinmay and then make Alex and Chinmay play tennis. This technique doesn't work. It basically, one of the people takes over all the identities and I become everyone, basically. So XX as Agent Smith in the Matrix movie, so it works like that. But if I wanted Neo also, Neo would also be me. Yeah. So there's still things we don't know how to do, is basically my point. But again, this is teaching a pre-trained foundation model a new concept, but without breaking its brain and thinking everybody is Alex, right? So that's kind of what is an open problem right now, as far as I know. So conclusions, and I guess we'll have plenty of time to discuss. So the first part of my talk was making better multimodal data sets, data comp. So on this effort, the challenge was engineering, okay? The challenge was, how do we run a face recognition on 13 billion images? How do we get the compute? How do we get the software engineering skills? How do we convince our students who want to just write 3 author papers to spend a year becoming software engineers? And the answer is with great pain and suffering. But the point is that once you create this tooling, we hope that now it's easier to experiment with large data sets and to kind of build a community on top of data set curation and data set filtration processes. Data set curation, which means building machine learning models to select the subset you will use to train other machine learning models, is, I think, going to be a very exciting emerging area. So I'll be glad to discuss this more if people are interested. The second part of my talk was, as I said, teaching foundation models new tricks. And we spend a little bit of time solving in painting with a latent diffusion model. And then I told you a little bit about this inconsistency issue that we discovered and added a new loss term to fix that. And I didn't talk about the ambient diffusion problem, so maybe I'll say a few words. Ambient diffusion means, is it possible by observing noisy images to learn the distribution of clean images? So think about this for a minute. It sounds impossible because my model has never seen a clean image in its life. It only sees images with missing pixels or images with noise. Is it possible to learn the clean distribution? If I know the corruption process, but of course I don't know the realization of the corruption. If I knew the realization of Gaussian, I would remove it, obviously, right? So shockingly, this is possible, okay? Shockingly, it's possible that you can learn a clean distribution even if you see a convolution. Actually, maybe with Gaussians, it's easy to see. Adding Gaussian noise means convolving with a Gaussian, right? So if you know you convolve with a Gaussian, in theory at least, you could deconvolve back and learn the clean distribution, right? So that's what this ambient diffusion paper studies. How do we learn a clean distribution by observing only corrupted data? And there's also a very related work called G-Sure by Mickey Alad's group that also appeared. Our method is related to Sure, but I think it's a different than Sure. But I don't fully understand the connections of the two. And future directions, briefly. So uncertainty quantification, I think, is a very important thing. So when we're running these methods to accelerate MRI, right? So we drop 80% of the measurements and we use a diffusion model to get an MRI reconstruction. Can you quantify for every pixel how much you trust it, right? And this is the same thing for any imaging problem or any inverse problem is obviously important. So I think this is a very interesting area. A second thing that's very important is reducing the training set memorization. So Tom Goldstein and a few others had papers showing that it is possible in stable diffusion to create some magical prompts that produce as output images from the training set, nearly identical, okay? This creates huge copyright problems, huge privacy problems, huge legal problems, and so on. So reducing the training set memorization is a very important area. We think that one way to mitigate this is to train with corrupted data, actually. So that's kind of our approach for that. But I think there will be a lot of research on this. Another area is personalizing foundation models. So as I said, foundation models are good for general concepts, but people will want their personalized stable diffusion for a number of reasons, or companies will want their personalized stable diffusion for seismic imaging or for MRI or for any problem they have in their own business. So, and they will not be able to or shouldn't train from scratch, right? If you're training an MRI model today, like you could start with stable diffusion. Stable diffusion knows all the images in the world. It's a very good starting point to to focus it on MRI, for example, rather than start from scratch. So I think a lot of people will be doing things like this. So how to actually do it correctly, nobody knows. Because as I told you, if you start doing learning, teaching it Alex and so on, everybody becomes Alex. So it may collapse in ways that you don't want and basically lose its generality. How to do correctly fine-tuning is an open problem, in my opinion. So it's a very challenging situation. And continuing on my rant on this, the word fine-tuning sounds like it's something easy. You just train it, just run it, no problem. It doesn't sound like an area of research, okay? But I think what is going to happen is all machine learning training will become fine-tuning. We won't call it fine-tuning. We'll find another name for it, specializing or focusing the model or parameter efficient, adapting the model. And you don't want to train the whole thing. You typically, I believe, want to create little MLPs, stick them somewhere in the transformer, and only train the little MLPs. Don't mess the weights of the whole thing. So I think there will be a lot of interesting research on this space. And another related issue is improving the diversity of the models, right? So if you're deblurring human faces and you take a photograph of your friend and it's blurry, and the Google deblurring makes them changes their race, as it has done, like that's a disaster, right? So making sure that the models are actually, having some fairness in the reconstruction is actually a very interesting problem. It's very real that they were super biased and they were basically making everybody white and young. So because that was the training set, of course, but also the algorithms amplified those biases, as we showed. So I will stop here and take questions. Thank you very much.
Very nice presentation. Maybe this is not relevant to what you're presenting, but when you talked about LMM,
Yes.
I forget the acronym,
Yes.
and ChatGPT.
Yes.
The part that struck to me was this, with respect to large language models, there is a spoken counterpart, spoken language models. And in my work, that is a lot richer than the images and cats and pictures of Alex. And so I don't know if you thought about extending that concept to speech signals and how it would look like.
Yeah.
I'm not sure if I made my point.
Yeah. No, of course. Yeah, it's a great question. So are there going to be multimodal models that combine language and audio, right? So maybe you can upload your jazz music and say, can you make this more like rock music? Or maybe I can upload my own talk and say, can you make my talk be in a Scottish accent, right? Or can you transcribe my talk and synthesize a better talk and in audio, right? 100%. I have no doubt that in 6 months or a year, OpenAI, for example, will accept audio as an additional modality, and it will also be able to synthesize audio, speech, for example. Like, so I think we will see things that you upload your own song and you say, I want this sung by Johnny Cash, right? And here is an audio clip just so you know who Johnny Cash is in case you don't, or it can be even somebody it can be somebody you recorded, right? So imitating the voice, imitating what is said, imitate like all these things. I have no doubt that there's 100 companies doing this as we speak.
So we're looking at May 2024.
I
can hold you up. You said 6 months.
We'll see. I think very soon. You will see. I mean, Whisper today is the OpenAI foundation model from audio to text. I can tell you, you upload an MP3 and it say transcribe it, okay? I can tell you that it's much better than I am. Like I'm not a native speaker. When there's noise and people are speaking English, I cannot tell exactly what they're saying. It's doing better than I am right now, and it's available through an API. So the audio to text is incredibly good right now. Now, if people have speech pathology issues or have very strong noise, or maybe in a cocktail party, maybe they're not perfect. I haven't tried, but we're making incredible progress, I believe, in that space. Yeah.
Sorry.
Thank you. Very interesting talk. I have a question about the where you mentioned about bad Z and good Z. You said that there are two types of latent code Zs, that some of them are the stable point of the VAE, but some of them we don't like. So based on my understanding, VAs, like typical VAs, tend to generate a normal distribution in the latent space. So is there any like insight in terms of distribution? Are those like bad Z kind of outliers of the distribution that they have in the latent space, or like two different distributions?
Great. Okay, cool. So here is a great question. So let's dive into this a little deeper. So first of all, you hope that the Z's are Gaussian, right? So the theory says if this thing was trained to perfection, it would be mapping an arbitrary pixel distribution into a Gaussian with zero mean and covariance identity. And now I would sample a Z from that and generate an image from distribution. That's what you would hope. In reality, that's of course not the case. And you can actually measure that. You can take 1,000 images from your distribution, MNIST or CIFAR10, look at their Z's, run a Gaussianity test, and that's one way to test. It's not going to be very good. And another thing is, if you actually want to make them better, we know several tricks that mitigate. You don't just sample a Gaussian Z and put it in an autoencoder. You won't get the best performance. You get okay. Now, the problem with this is a beast model, right? It's a very big model. So anything, and the distribution is incredibly complicated because it has anything on the internet, right? It has MRI and dogs and cats and spectrograms, and who even knows what's in lion, right? So this is an empirical discovery. So if we think theoretically, what should an autoencoder do? Every natural image, every image from the distribution should have a unique Z, right? And then every Z should produce images only in distribution. But this is not the case for this model. For this model, you can, if you pick Z's, especially if you try to pick bad Z's, you will get very bizarre images that are not in the training set. And therefore, we start with a theoretical idea, and then we test something small, and we say, should this be happening? Should there be Z's where the decoding of Z and the encoding of that again is completely different from Z itself? In theory, it shouldn't. In practice, there are. So we just add an extra term to fix it. So that's kind of the pipeline. But yeah, this is an empirical discovery. It shouldn't be happening in theory. Yes, great point.
I have a question, Alex. So thank you for the great talk. In the beginning, you mentioned this idea of using clip to filter data,
yes,
and get better data, and then training the next model of next clip, and then
yes,
repeat the cycle. So I was maybe asking a philosophical question as to whether this curve of increasing performance, is it concave or convex? Meaning that do you think you'll reach diminishing returns very quickly if you repeat this process multiple times, or do you think you'll keep improving?
So I think what is happening is not exactly, I think there is a bootstrapping process happening. So DALL-E 3, for example, so DALL-E 2 was trained on a data set of images and captions. Then DALL-E 2 can be used to create synthetic data, right? Now, once LMMs came out, like there's also public LMMs, by the way, like Lava and Blip are models that you can download today, upload an image, and ask questions about the image. One thing you can do now is you can take Lion, you can take an image from Lion, upload it on Lava, and say, describe that image with a lot of details. So you can write a long, so it will just spit out a big text and then say, what's very particular about this image? It will give you more text. So now you have all this big text. That's a new caption for your image. an expanded synthetically generated caption for your image. And as far as I know, DALL-E 3 was trained with such synthetically generated captions that they use basically an image captioning model. So there's a bootstrap process where a model is used to filter, create a synthetic data set that's used to train a better model, that's used to generate new data, that's used to train a model, and so on. So there's an alternating process, I believe, between creating or augmenting data sets and training better models on top of them.
Does it reach diminishing returns very quickly?
I don't think anybody knows. I don't think anybody knows. I mean, it also depends on diminishing returns in terms of what? In terms of compute. And even compute, the benefit of compute is you don't have to pay all the compute. Like, not that the same person is paying all the compute. That's another thing about it, right? So if I can leverage Stable Diffusion right now and write an in-painting paper, I didn't pay, $10 million to train Stable Diffusion. So there's a lot of bootstrapping this compute that has gone into the foundation models, I think. So it's hard to measure costs, yeah.
Hi, that was a really good talk. I just had a couple of questions. So first, in terms of image denoising and painting, how does this compare to just the classical methods like doing total variation minimization or PDE-based or like in-painting methods? And do you compare to those?
Yes. So good. So let's see. So remember the central dogma? So the central dogma is here. I think you're saying, so, okay. So the short answer is, in the world of denoising, there is a gazillion classical techniques and a gazillion deep learning techniques. I think Peyman yesterday had a very nice overview of the history of the pre-deep learning techniques and the deep learning techniques. Usually the deep learning techniques are obviously much better than the pre-deep learning techniques because they're data driven. Now, in the world of deep learning techniques, there are deep learning techniques that respect my central dogma that we are going to refer to as unsupervised techniques. And then there is supervised techniques. Supervised techniques simply means, oh, you want to remove Gaussian noise. I'm going to take a data set, take an image, add Gaussian noise to it, and train a UNet to go from the noise image back to the original, right? And then there is, of course, many more cleverer ideas building on a matched data set. So the real question to me is, do you need a matched data set, which means corrupted, non-corrupted, corrupted, non-corrupted, or do you need just a data set of non-corrupted? If you're only using a data set of non-corrupted during your training procedures, you are in the unsupervised world and you are respecting my central dogma. In that domain, in unsupervised denoising techniques, the one I showed you is the best by far, because it's using the best prior, until Peyman came out 2 weeks ago and did much better because they also used an extra trick called prompt tuning. In the world of supervised techniques, in their domain, they are the best. So in general, supervised techniques are very good at doing what they were trained to do, okay? So if you want Gaussian noise and you want to do it on CelebA, train a supervised method on CelebA for MMSE, you're going to crush everybody else. Whoever has the biggest network wins, right? But if it's not exactly Gaussian noise, or if it's not exactly CelebA, now you face the fragilities of the supervised method. So the reason my central dogma exists is because I say you don't actually want to solve the problem you exactly trained for in reality. You have variations in the acquisition process, variations in the anatomies, variation in all kinds of things you don't account for. So that's kind of the separation. But the short answer is supervised methods in their domain are crushing everything else. They have been crushing it forever. And that's why it's so hard to publish in the space with unsupervised.
Okay, thank you. And then I was also wondering, so when you feed like the XXX is playing with dogs, and then you want it to learn that it's you, are you optimizing over, so is XXX changing over time?
Great.
Or
great.
Yeah.
So, okay. So again, I summarized a lot of things here, but let me dive more into it now. So, all right. So the this idea, in the simplest form, that's called textual inversion. That was not invented by me. You just train the one vector and use the same vector across all noise levels, which is all times. Our actual paper, which is called multi-resolution textual inversion, says exactly what you said. Don't train one vector for all noise levels. Train a different Alex at noise level 1, a different Alex vector at noise level 0.5, which corresponds to multi-resolution. It's like one vector learns the blurred high-level outlines of my face, and the other one learns the details of my face. So the multi-resolution aspect is a refined way to do this textual inversion. And right now there's Dream Booth, which is the Google version, which has extra tricks. And there is LoRa Dream Booth, which is yet another even more advanced method for doing this. So there's a whole ecosystem of papers doing this right now.
Yeah, but there's no way for me to just type an image of and then a string of random letters and then have it produce your face.
Unless you fine tune it, no.
Okay.
No, absolutely not. No. Oh, I see. You're saying like an adversarial example.
Yeah.
Okay, I see. Yeah. So good. That can happen, but not for an. What we did, we tried this. We tried some gibberish words. And sometimes gibberish words in Stable Diffusion or DALI, it was in DALI we were experimenting, sometimes gibberish words consistently correspond to real concepts. And the reason this is important is DALI, for example, has all these pre-filters for pornography and for violence, right? So if you try to generate an image that has violence, it will filter it. The way it filters it is it analyzes the text. But if you can type some gibberish and get, violent images, effectively adversarial attacks in the text latent space, you can circumvent those protection filters. So we found this, and we had a paper about that. It's called the hidden vocabulary of DALI, where gibberish corresponds to concepts. And we notified OpenAI about this. And there's other ways, of course, you can look at the image and try to detect violence and pornography also. So that's one way to mitigate. But yes, that's a good point. There's adversarial attacks you can do to this.
Okay.
Great point.
Thank you very much. That was a really good talk.
Thank you for the great talk. So in solving linear inverse problems, the basic idea is to leverage the foundation models as a prior. So my question is that, how do you know your foundation model is a good prior for the problem you want to solve? So what if there's a big bias for the prior?
Yeah, great. So the short answer is through this. You measure so you take an inverse problem where you know the ground truth, you corrupt, you reconstruct, and you look at the mean squared error, the LPIPs, and the S-same of the reconstruction. And if you are in distribution, that's a fair test mechanism of evaluating your inverse problem. You can also fine-tune your foundation model into your domain. But what we have found, at least so far, is basically if there is a bigger foundation model being published, you should just use that or start from that. And you're just riding a wave of incredibly powerful foundation models that are trained by everybody around you now. So training our own from scratch has been much, much harder than starting with big foundation models and maybe fine-tuning them in some domain these days.
Okay, thank you.
Okay.
Hi, Dr. Dimakis. Thank you. That was an excellent talk. Really enjoyed it. I had more of a philosophical question. What challenges do you foresee in making LLMs for medical imaging, especially considering PHI and other challenges that exist within the medical imaging domain? What challenges do you foresee for making LLMs in the future for medical imaging?
Yeah, great question. I think the biggest problem is the availability of high quality data sets and also vetting benchmarks. So the data set is one thing, but also agreeing on the benchmark and saying, okay, here's what we're going to do. Here's the metric. Here is, so I think the benchmark obsession, when I got into machine learning, I was kind of bothered with the benchmark obsession, right? So it's like, okay, I don't care about ImageNet, top one. It's very difficult to play that game. But once you find a narrower domain and you agree on a benchmark, the benchmark is really driving progress. So you really all agree, okay, that's what we're going to measure, and then it's much cleaner how to publish. So I think benchmarks and data sets are the key things that need to be developed to make progress in what you said. Yes.
No, it's okay.
I just want to follow up with the question and your answer. That's where the rub is. Who gets to decide the benchmarks? Most of the experts, the clinical experts, if you put 3 of them together, there are at least 4 opinions as to what makes sense, what doesn't make sense. And it's definitely not in the realm of us signal processing engineers and computer scientists. It's not in our domain. So do you have any idea as to how to get to that?
Yeah, great question. So here's what I believe, and maybe it's a little controversial, but I have seen this problem in every domain that I work with, right? So when we do deep learning, for example, deep learning or in painting, we have agreed to do MSc, LPIPs, and SSIM, right? Okay. Why have we agreed? Because the previous paper that was published had those and got accepted in EURIPS. So now if I beat it fair and square, I will also get accepted to EURIPS, right? So like it's a sociological issue. Now, I don't think this is the best way, but in fact, benchmarks are very flawed. Like everybody knows, for example, that MSc is actually a terrible metric for de-blurring. In fact, MSc encourages blurring, right? Because the best images are always going to be the blurriest. That's like your model hedging its bets. It doesn't know what the pixel should be, so it guesses the average because it has smallest mean squared error. However, what we have found in all the domains that we have experimented, so in data comp, for example, because of this issue, I'll just talk about that for a minute. So in data comp, we said, okay, how do we evaluate a model, right? So you have done a filtration, I have done a filtration. How do we decide which one is better, right? And as I said, we ran code, we created code and benchmarks for 38 benchmarks, okay? That's like a ton of work for our students to get all those data sets, write all this tooling, produce all these evaluations. What we have found, and this was on Twitter yesterday, is that ImageNet zero shot, if you plot ImageNet zero shot on one axis and the average of 38 benchmarks on one axis, you see basically a straight line, okay? So ImageNet zero shot sounds like a very stupid thing to do. You literally say, it has never seen the ImageNet classes. You just say a type of a dog, an image of a dog, an image of a cat. You just measure. That's how ImageNet zero shot is evaluated. Has nothing to do with medical imaging or fairness in recognizing people. Yet, shockingly, in practice, ImageNet zero shot is super predictive of, so if ImageNet zero shot of model 1 is better, then all the other metrics on average are better. There's very few exceptions. So ImageNet as a benchmark has driven progress in the correct direction, even though it's a stupid benchmark, right? And I think that's a power of benchmarks, is that even if they're not perfectly measuring what an expert would say, they are driving progress. And until some point, they're not. Like if there is a point where the best model in the benchmark is this, and then the radiologists say, this is producing trash, please stop using that benchmark, then you write a paper that says the benchmark is broken, let's change the benchmark, right? So I think it's a collective sociological process in our community where we decide the benchmarks and then we decide if the benchmarks are working for us. But so far in this world, ImageNet zero shot, for example, has been shockingly effective at measuring progress. The same thing with FID. FID is a metric that measures how good the generative model is. If I tell you how it works, it's incredibly bad. Like the way it's done is incredibly naive. It basically fits a Gaussian and looks at the Gaussian distance in the latent space. But it actually works. Like when the models produce better images, when I see them, humans see them, and they correlate the human evaluation with FID, it actually is correct. So it matches human evaluation for generating images. So even though it sounded very naive, it matches outcomes of human evaluators and therefore is a useful metric. So to me, that's the value of a metric.
So thank you for the nice talk. I have a question to this consistency analysis for diffusion models you did. I was wondering, why is the diffusion model denoising stochastic in the first place? Because, for example, if I take MMSE, I know it will be a deterministic mapping. So why is it stochastic? And could it also be deterministic in the first place? And then I don't have this consistency issues.
Yes, good. Okay. So again, I was very fast here, just basically pointed to the work, but you raised a good question. There is two types of denoisers: running the SDE, which is a stochastic process, or running the OD. Or basically, it's a type of distillation that people are doing where you train a model from the noise image to give you directly the denoised image, okay? So the question is, if you just run the SDE multiple times from a very, very noisy image, you're going to get very different images. And then when you average them together, you're going to get a very blurry image, okay? The theory says that this very blurry image should be the conditional expectation of x0 given xt. The conditional expectation of x0 given xt is the best MMSE denoiser, which is very blurry when t is very high. So this is telling you that in order to test how good your denoiser, your E of x0 given xt is, run the SDE multiple times, average the outcomes, and see if that is truly the same outcome as the MMSE denoiser you learned. So both of them are noisy, or both of them are blurry, if I'm answering your question. But the point is, now if you had a deterministic denoiser, an OD solver, that's the other concept of denoising, of consistency. Consistency models by Song et al. Studies what you say, I think, whereas we study the stochastic one in our paper. So there's basically two related papers. I'll be glad to follow up online with more details. Yes.
All right, we're getting close to the amount of time we have allowed for the plenary. So let's thank Alex again.
Thank you.
And just to remind everyone, we have a coffee break until 3:30 when the next sessions will start.